Welcome, all of you, back after, I hope, a refreshing coffee break and also some interaction and networking that you have a time for. This is, for me, the grand finale of the Battery Innovation Days, even though we have some exciting topics also coming up tomorrow. But today and now we are to celebrate our Young Research Award, and that is awarded Ana Cristina Martínez Maciel. Congratulations. Well
Thank you very much.
And I'm Kristina Edström. I'm Professor of Inorganic Chemistry at Uppsala University in Sweden. I'm also the coordinator of Battery 2030 Plus. This award was sort of announced a number of months ago, and the whole of Europe have been able to submit suggestions and nomination for this prize award for young scientists. And with young scientists, we mainly mean PhDs and postdocs all over Europe. And you don't need necessarily to be European, but you should have your thesis or postdoc in Europe. So that was the sort of limit for this. And we have received a number of nominations. We have received theses, we have received letters from supervisors. We have also received a small film pitching the person who is nominated. And we have been a nomination committee looking at the suggestions. And this nomination committee have been representatives from the 5 organizing committees here for this Battery Innovation Days, which means, of course, myself, then Battery 2030 Plus, but also representative for the Battery Partnership, BEPA, or BAT for Europe, the association, Batteries Europe, our ETIP, our holistic networking hub, and the 2 IPSHEs. And this has meant that the people in this committee have had very different backgrounds. But we have had a set of criteria for our selection. We, of course, look at the topic, how well it's motivated, what is the goal of the thesis, how are the conclusions presented, and how have the studies reaching the conclusions been undertaken. So it's also reading the thesis and thinking about it and looking at it. We have more looked at the quality of research as such, not so much what the topic was. So it should really be novelty within this topic that was the selection of the thesis. And we were like 7 people looking at this. We had some extra people also than from all these initiatives. And we were anonymously sure that the one we should really award the prize is our young Ana Cristina Martínez Maciel, sitting here today. She has written a thesis about nickel-rich NMC materials for lithium-ion batteries, surface reactivity and gas production. This thesis was done at Amiens in Université de Picardie Jules Verne, and together with the Renault Group. And it has a lot of fundamentals in it, but it's also useful fundamentals for the application. And it will be really interesting to see the presentation coming up. What I also appreciate specifically with Anna, that is that she is an Alice Storierai alumni. She is actually one of the MESC students that we have in Europe, which is really a gold mine for competencies in Europe, spread all over Europe today. I just told Anja I had myself PhD student from MESC number 1, and Anja she was in MESC number 12. So from all of the battery community in Europe, all these initiatives, huge congratulations. And I would like now to leave the floor to you to give your presentation so we can see what kind of work you have done. And I also would like to inspire you all to ask questions in this chat, so that, because we will end this by having a Q&A, so Anna can really show and excel what she's doing. And please tell us also what you're doing now, because I know you are in Texas. And you have promised to celebrate this thoroughly tomorrow when it's Thanksgiving in US. So I leave the floor to you. Congratulations.
Thank you very much, Dr. Edstrom. It's a great pleasure for me to be here. I am very happy, very honored to be receiving this prize today, to see that my PhD results, my PhD research, actually it's having the fruits. Yeah, as the Dr. Edstrom was saying, I defended my PhD thesis early this year, and then I moved to Texas for a postdoctoral opportunity. I will talk at the very end of my presentation. I will have one slide to talk about what I am doing today. And so this presentation will be around 25, 28 minutes. And can you change to the next slide, please? Yes. So the title is Nickel-Rich NMC Materials for Lithium-Ion Batteries. This is a surface reactivity study and its relation to gas production. So this thesis was part of an industrial and academic convention. So this was done in France as part of the CIFRE program. I was very happy to be selected to be part of it. Because this is how the industry is actually connecting with the academia today. My thesis advisors were Stéphane Laurel, Sylvie Grosjean, Pierre Trambin, and Bruno Delobel. Bruno Delobel was in fact a MESC alumni as well, MESC 1. So I was very proud to work with him. So next, please. So today I will talk about the context of the study. Then I will talk about surface reactivity study of nickel-rich NMC materials, and then how this reactivity study relates to gas production, a very hot topic in batteries for electric cars. Then I will conclude and present some perspectives, and at the very end, I will talk about my work today. So to start with the context of the study, we know you have heard in previous sessions, almost in every conference today, that the global warming is an issue. The global temperature has risen over the last year in a very alarming way. And this is because of greenhouse emissions, among which CO2 represents around 70% of the total volume of gases. If we talk in particular about the emissions in France, you will see that the transportation sector is the one that pollutes the most. So one of Renault's mission is to contribute to decrease this CO2 production by implementing a wider range, options of electric cars. Next, please. So I will talk very briefly about the battery pack, but I'm sure most of you already are aware of this information. So in the particular case of Renault Zoe, one of the best-selling electric vehicles in Europe, the battery pack is located at the bottom part of the car, and it is composed of 12 modules. A module looks like this, and it is composed in the inside from pouch cells, and the pouch cells are just regular stacks of positive and negative electrodes separated by the separators soaked in electrolyte. The requirements from this battery pack are to be low cost, to be safe, to have long cycle life, and of course to have high energy density. So high energy density is particularly important for the automotive industry because this is what will define the driving range. And for us chemists, what limits the energy density is regularly, most often, the positive electrode. Next, please. So if we talk about positive electrode materials, there is a wide range of materials that have been used. For example, LCO, NMC, NCA, LMO, and LFP. And if you see the trend from the last years up to 2030, you will see that the use of these materials will only increase. And if you see the distribution of materials, for example, in the year 2030, you will see that NMC materials, they dominate the use of positive electron materials. And this is because they are used in electric vehicles. And of course, for a battery pack, we need a lot of material. Next, please. So what are the NMC materials? So NMCs are lithiated oxides of nickel, manganese, and cobalt. And we refer to nickel rich when the nickel content exceeds 0.5. Some says 0.6, which is also valid, of a molar content in transition metals. So if we position the three transition metal in a ternary phase diagram, you will see that the trend from for the last years has been to increase the amount of nickel. And this is because the nickel content is the one that will increase the energy density, and as a consequence, the driving range. If you see this phase diagram, you will see that we want to get away from a high amount of cobalt because of its price and its concerns due to destruction. And also, we want to have a low amount of manganese because we have capacity loss, just because the redox couple is not active in the potential range. So it has been currently, for the last years, this trend of increasing of nickel content. However, this has a disadvantage, which is the durability of the batteries. It has been observed that when a higher nickel content is used, for example, 811, the durability is reduced. And very often in the literature, it is said that this is because of the surface reactivity. So the question for my thesis was, how is the surface reactivity affecting the durability of these batteries? So for this, the next, please. So for this, I show you here the two sources of the surface reactivity. So one is the delithiated state of NMC. So we know, it is known since years back, that when the NMCs are in the delithiated state, this means there is depletion of lithium in the lithium layer. These structures will tend to collapse into a rock-solid structure with a production of active oxygen. The problem is that active oxygen will then oxidate the electrolyte and produce gas. And the other surface reactivity issue is occurs at the pristine state of NMC. So we know that NMCs, they are sensitive to air, and this is especially important for high nickel. And as a consequence of this air exposure, they will produce carbonates, hydroxides, and oxides. The thing is that the mechanism was not clear in the literature. It was just assumed that they are produced. But it is very bad because as a consequence of this air exposure, there is capacity loss and gas production. So because these are surface reactivity issues, we will see impedance increase, of course, gas production, as I said, capacity loss, and this is what affects the durability of nickel-rich NMCs. So for my thesis, the objective was to evidence the reactivity of nickel-rich NMC materials through the study of surface species evolution to clarify the mechanisms, and through the gas analysis upon high temperature storage in the delithiated state. So for this, we use 5 different materials ranging from 0.5 to 0.9 of nickel, and they came from Umicore. One of them was a coated material, the 622C. Yes, next, please. So let's go with the first part of the results. So I wanted to study the surface reactivity of these materials, right? So for this, I needed a protocol that didn't exist in its optimized way. So it basically consists in solubilizing the surface species on NMCs, separate on one side the wash powder and on the other the solution containing the surface species, to finally analyze the solution either by pH titration that detects carbonates, hydroxide, or by inductively coupled plasma and atomic absorption spectroscopy. We encountered some problems, of course. There was acidification of the solution. There was lithium proton exchange on the surface of NMC. So we had to optimize various parameters, such as the atmosphere, the water quality, the agitation time, the mass ratio NMC to water, to at the end obtain a very reliable protocol that gave us reproducible results. Next, please. So with this protocol, we obtained several results. I will just show one of the most important ones. So in here, you can see that the results of acid-base titration of a received NMC surface species, and also a surface species coming from an exposure to water and CO2 for 6 days. So we did this in the control atmosphere, so it was reproducible. Imitating the atmosphere that the films will see in a factory, right? In an exposed dry room, we can say, where they kind of control the humidity amount. So on the left, on the received NMC, you can see the amount of carbonates and hydroxides that are on the surface of these NMC materials, of the 5. You can see that the amount of carbonate is almost constant. However, the amount of hydroxides that later we discovered is not hydroxide, it's lithium oxide. The amount of these hydroxides is increasing. And then when we expose these materials to air, to this controlled air atmosphere, you can see in the picture how the surface really changed. So this means that something is coming out from the structure. It's not only the air that is reacting. So you can see that the amount of carbonates is increasing with the nickel content. So for 901, it has a lot of carbonates produced on the surface, which implies that there is a deletion occurring. But in the literature, it was not clear how. So next slide, please. So what we did was to analyze all of these materials. So the 10 of them, they are received on the left and they're exposed on the right. By thermogravimetric analysis coupled with mass spectrometry. So on the left, you can see the result of heating the 5 NMC materials up to 900 degrees. And you can see there is a huge weight loss from 600 degrees, which is normal. It's related to the production of oxygen, as you can see on the reaction on the bottom. So it's the regular thermal decomposition of NMC materials. So the received were just used as a reference, what we have at the beginning. And then the exposed materials, they were very interesting because they present this huge weight loss above 600 degrees, but they also present a weight loss in the range of 150, 450 Celsius degrees, which does not correspond to the decomposition of carbonates, because that one occurs at 700 degrees, and also does not correspond to the decomposition of hydroxides, because that one occurs at 500 degrees. So what is going on in this temperature range? So for that, in the next slide, I'm showing the MS, so the mass spectrometry results of this temperature range. So what we can see here is that we are seeing a production of water, of oxygen, and CO2. So after some calculations of this specific part of the spectra, we were able to deduce this equation, which is how the NMC materials are decomposing upon water and CO2 exposure. So we propose that at the surface of NMC, we are producing lithium carbonate, an oxyhydroxide of nickel and cobalt, and oxides of nickel and manganese. And we support this reaction on the fact that reaction number 1 here says that the oxyhydroxides, they will decompose into oxides, water, and oxygen, which is exactly what we see in the graphs, water and oxygen. And then reaction number 2 says that when we are heating a material that is degraded on the surface by air, we will produce the oxide, so we will reform it, and we'll produce also CO2. And the CO2 is exactly what we see on the top right. So from this study, we were able to propose this mechanism that hasn't been reported before. We were able to prove that active material is lost upon the storage of these NMCs on this air atmosphere, and also that the degradation is actually aggravated by the increasing nickel content. As you can see that in these graphs. So with this information, to summarize, the received materials, they contained a surface species on the surface. This is normal, but what is very bad is that upon air exposure, even the slightest bit of air, they will produce oxyhydroxides, oxides, and carbonates, which is bad for the capacity loss and because also they increase the impedance. So with this information, what we wanted to see now is what the effect of the surface species in a battery. So for that, the next slide, please. So for that, what we did was to artificially store the materials, either the NMCs as received or after exposure, or the pure materials, carbonates, hydroxides, or oxides, with electrolyte on a blue bag. Then store these at low or high temperatures that are correspondent to what a car will attain. And then separate the powder from the electrolyte and analyze the electrolyte with NMR, with nuclear magnetic resonance of fluorine. And the results, so I will just show you one result because of the time. But this is what I think summarizes the best, because carbonates are always at the surface of NMCs. So this is a result of storing a lithium carbonate with electrolyte and heating at 25 or, well, storing at 25 or 55 degrees. We see that there is a doublet peak of LiPF6. This is normal. It's contained on the electrolytes of commercial batteries. And then we also see a doublet that corresponds to lithium difluorophosphate, so LiPO2F2. And we see that the production of LiPO2F2 is actually favored with temperature because the peaks are, the ratio with LiPF6 is higher. So we were able to deduce that the surfaces battery conditions, they will react with the electrolyte to produce, in particular with LiPF6 in the electrolyte medium, to produce LiPO2F2, LiF, and other gases. So we are seeing constantly gas production, right? Gas production. So this is the point where we started to making the relation between surface reactivity and gas production. But let's come back to LiPO2F2. So after a fast search in the literature, I saw that LiPO2F2 has in fact has been used as electrolyte additive, and after talking with the industrial partners, yes, it has been used. Phosphates in general has been interesting in the industry for some years now. So that's why we decided to test LiPO2F2 as electrolyte additive. So this is one of the results that I obtained. I dedicated one chapter of my thesis to this, so today I will be just very brief. We see that, in fact, after a number of cycles, in this case, these were pouch cell 622 graphite, after 200 cycles, we can see that, indeed, when the additive is added, the capacity retention is better. Now, what we asked ourselves, because my thesis was all about mechanisms and chemical reactions, what we ask now is what is the mechanism through which this additive is working? And that is how, next please. That is how we performed several studies. We did one of the interfaces and another of the electrolyte. From the interfaces, we learned that there is no apparent effect on the cathode electrolyte interface. Right now, we are hearing a lot about cathode electrolyte interfaces. In our case, there was no effect. Possibly, there is only LiF. And on the solid electrolyte interface, there was an effect. So we saw that it is heavily enriched with phosphates when the electrolyte LiPO2F2 is used. And then regarding the effect on the electrolyte, we saw that oligomers, so this molecule that you see on the top right, these oligomers were not formed when LiPO2F2 is added. So this is how we were starting to see what is the mechanism of this additive. So the equation in blue, so without LiPO2F2, we see that normally the radicals form upon the first reduction of the battery, so the first charge. They will produce through several reactions these oligomer molecules. But when LiPo2F2 is added, these radicals will be trapped by the LiPo2F2 and will produce only the phosphates that will enrich the SEI, and also LiF that will be also deposited on the surface. Next, please. So as a summary of this part, the as-received materials, so they contain the surface species that we talked about. Upon exposure to the electrolyte, so in battery conditions, they will produce LiF on the surface of NMC, LiPo2F2 that can be dissolved into the electrolyte, but also can be retained in the surface and other gases such as CO2. The effect of LiPo2F2, as we saw as electrolyte additive, was mainly on the negative electrode because it reaches the SEI with LiF and organofluorophosphates. And of course, this will lead to less electrolyte aging. So this part was important for us from an industrial point of view because we are using something that was on the surface as electrolyte additives. So we don't have to add it artificially, right? It is being produced inside with the electrolyte. The additive is being produced in situ. So this was very important for the industry. So we are using something that was normally deleterious for the NMC. So this is why this was important. So now that we have been gas appearing everywhere, this is the time to relate the surface reactivity with gas evolutions. So for this, just as an introduction, we know that NMC materials, they produce gas, even if normally it's not acknowledged. There are surface reactions such as chemical and electrochemical oxidation of carbonates that produce CO2, active oxygen as well. And there are also this structural transformation of the lithiated NMC that produces active oxygen. So the objective of this part was to evidence the influence of the nickel content. So because we are talking about high nickel, nickel-rich materials, on gas evolution. So for this, we used laboratory scale Podge cells. We did NMC, either 622, 811, I will show you when they come. And we implemented a septum through which we could extract the gas safely. So after some cycling, then a storage period followed, and the gas was sampled out after the storage period, because we are trying to see the effect of temperature as well. So one of the results, next please. One of the results that we observed from this gas analysis, so it's here, is I'm showing you Podge cells 811 graphite, but the 811 was used either as received, so it's the dotted lines, or in the exposed form. So it means after it has seen air during the battery production. So you can see that, next please. You can see that the three formation gases, so CH4, C2H4, and C2H6, they are almost constant, regardless of the surface state of NMC. This is normal because, in fact, they are produced from the first charge of the battery. So they are not really related to NMC at this stage. Then I will show you after something very interesting about them. They are just increased by temperature and by rate. Next, please. On the contrary, CO2, you can see that there is a huge difference when NMC exposed or as received is used. So this is because first, there is thermal degradation of the electrolyte because we did this at 55 degrees. But this shouldn't make this difference, right? So what we saw is that there are electrochemical reactions of the carbonates and also chemical reactions of the carbonates. We did several experiments to try to differentiate both, to see which is predominant, so to tell to the manufacturers which is worst, in fact, temperature or the first, cycling. So unfortunately, we were not able to dissociate electrochemical from chemical reactions, but they exist. What we were able to do, because this CO2 also depends on a state of charge, which is this slide, what we were able to do is to do an experiment in which we store the battery with the NMC either in the delithiated form. This means in the charged state of the battery or in the lithiated form. And we can see the huge difference in CO2 amount when the battery is stored in the lithiated, in the charged state. So it is a fact that NMC materials, the state of charge influences the amount of CO2, but we were not aware of how important this is for nickel-rich materials. So this result is also NMC 811. So you can see that CO2 is double when the battery is stored in the charged state. This is particularly relevant for the industry because this is what sets limits of potential. So up to which potential we can cycle safely without producing CO2 that is actually coming from the NMCs, from its chemical instability. So if you like the reactions, the reason for this is on the right. In fact, the NMCs, they tend to reduce and produce active oxygen in their discharge state because, as I mentioned some slides ago, the structure will tend to collapse onto a rock salt structure. And this oxygen will oxidate the electrolyte and produce CO2 and CO as well, but I didn't show that today. So we see the clear contribution from the reactivity of the lithiated NMC to total CO2 production. Then we also wanted to evaluate the influence of nickel content. So we compared the gas coming from after some cycling of 622 or 811 and the gas coming after cycling plus storage. Next, please. So what we saw after the formation cycle, so after this cycling steps, was that the CO2 coming from 811, from the pouch cells containing 811, was higher than the one coming from 622. But we were able, through some other experiments, to deduce that this is due to the electrochemical oxidation of EC, of ethylene carbonate, through this reaction. So this is how NMC composition actually influences CO2 production. And then, in the formation, after the formation of these cycling steps and the storage, we saw that, in fact, one of the gases, of the formation gases that we thought had nothing to do with the positive electrode, actually was being consumed. So we repeat this just to make sure that this was not something that was once in a batch. So we did this on several batches, and we were able to see that the ethylene gas was in fact being consumed. After some thought, we deduced that the active oxygen being produced from the NMC we proposed that could come and oxidate the ethylene and produce these gases from these reactions here shown. So there is something very interesting there, because we are talking about crosstalk inside of the battery. We know that the batteries are complex systems, but this hasn't been reported before. So this demands further investigation. Unfortunately, I didn't have the time, so I did not went for it. But I know Renault, they are very interested in understanding these gassing issues effects. So this is how the nickel content influences the gas production. So this is a summary of the reactions that I dealt with in this part of the gas analysis. So we knew the gases that come from the graphite electrode. Those are very known since years. And now what I was trying was to differentiate the different gases coming from the NMC particles. So we have chemical, electrochemical reactions, chemical reactions coming from the lithiated state, electrochemical reactions with the solvents, but also in the electrolyte, we saw that there are crosstalk reactions, chemical oxidations, thermal degradation. So the bottom line of my thesis is that batteries are very complex. There are a multitude of reactions that we cannot always control specifically. But at least if we were to study the NMCs, we saw that there are ways in which we could decrease the gas, at least coming from the NMC materials. So to conclude and give some perspectives of my work, so let's come back with the surface reactivity study. So the received materials upon air exposure we saw that they produced on the surface hydroxides, oxides, carbonates. We proposed a degradation mechanism for this, and on battery conditions, we were able to see that the surface of the NMC materials, they will also change. LiF will be produced, LiPo2F2 will be produced. We proposed LiPo2F2. We proposed to leverage LiPo2F2 as an in situ battery additive, just to take advantage of what is already on NMCs, on nickel-rich NMCs, and which also has an effect on the negative electrode. Then regarding the gas, we saw that the surface reactivity of the nickel-rich NMC exacerbates gas evolution as a function of nickel content. This is especially true for the highest nickel content materials, and that this is a complex system. So there are a multitude of gas origins, as I enunciate here, and that they should not be disregarded. So we should always consider each of the different gas sources. So there are a lot of things to do still, of course. My thesis ends, but the topic doesn't end for the industry. So in terms of surface protection, there is work to be done on cathode electrolyte interfaces additives, so to protect the nickel-rich NMC materials. There's also additives that can be used to trap the active oxygen that is produced at least from 3 different sources related to NMCs. In terms of the bulk material, there's work to be done on surface coating, on dopings. I know one of the person who was on my committee, she was actually working actively on this topic. So it's something that is also very, very hot. To explore different NMC textures, so we used polycrystalline NMC from Umicore, but I know they are commercializing already single crystal NMC, and it's being also seen as a very big possibility to avoid this surface reactivity. As part of my thesis, I also did an impedance study that relates to gas, and there is a lot to be done there. There is a huge relationship between impedance and gas evolution. I think that's also a big topic that can be studied. And finally, at the industrial level, we need to strengthen partnerships with the laboratories, because this is how the industry actually will know why. Because sometimes, even if the industry, even if they do scientific research in the innovation and development, is not the same as actually a laboratory that is research-oriented, not commercialization-oriented, actually understands the why. And also because this will allow the industry to constantly update their database into the recent novelties. So I want to thank a lot of people that contributed to this work. This is a picture of the people that was in the same laboratory in Amiens, LRCS. To my 4 advisors, they were super helpful all along this project, even despite COVID happened. So I want to thank a lot of people. And finally, I just want to take 1 minute to talk about I think I was a bit long. Sorry, is that okay? I want to take just 1 minute to talk about what I am doing today. So I am working at the University of Texas at El Paso. I started in March. And we are working on the resin formulation for the 3D printing of batteries. So we have been recently hearing a lot about 3D printing, and this is because additive manufacturing, colloquially known as 3D printing, it will allow us to create complex shapes of batteries that doesn't follow this stacking or rolling architecture, but will actually be fixed into a particular object. For example, the frame of glasses, or the frame of a watch. So we will have complex structures. There is a lot to be done. We are a big team. This is just some of the people I work with. We have a lot of ongoing collaborations, and we were recently awarded an internal NASA grant to develop sodium-ion batteries, in this case, from lunar regolith, and by using 3D printing as additive manufacturing technique. So thank you very much. That's all from me. If you have questions, I will be happy to discuss.
Thank you. I'm applauding you from the whole audience and congratulating you again. And the chat is full of congratulations and hearts for you and so on. But we have a starting question, which is a bit tricky. And it's to do with this market and industrial innovation uptake. You have an education from Europe, and now you are in US. Will you bring your expertise to European companies or American?
Very tricky indeed.
That's about your future. Where do you end up in life? And that's not so simple.
No, it is not. I will have very happily stayed in Europe. Renault, they have opportunities for me. I was very interested in staying, but there were two reasons why I had to leave. The first is that my husband was getting a Fulbright scholarship in US that is so prestigious that we couldn't say no. And the other is that I wanted to diversify my vision. So I wanted to see what is being done in the US. So I could actually compare and see what's best for me, what's best for my professional development. And so also I could bring this to Europe, of course, because they work in a different way. I mean, in general, research is the same, right? But mentalities, they are quite different. So I wanted to take the opportunity to enrich myself with this experience and actually one day bring this to Europe. It's still in my plans to come back to Europe. My husband, he's French, so it's natural that we come back, but I just don't know how. It's been so enriching in the US, the experience, that if there is a very good opportunity in Europe, for sure I will take it. But so far, we are evaluating the possibilities.
I think it's very good that you are going out and gaining and broadening your experience. And then we bounce the question back to the one who asked it and say, give Anna a good offer. She's here. She's brilliant.
Right.
Take the opportunity. Now, I think it was interesting that you say that the work is the way you work is different. Can you describe the differences? Is there anything we can learn from that, you think?
Yes, I think, well, maybe I have, my experience comes from one laboratory, one particular company, so it may not be applied to everything. But I think in France, they are very good in research, in engineering, applied research. And this is great. And I think in the US, they worry a lot about publishing fast and not necessarily very high quality research. How to say? They search to commercialize, to produce. Maybe I'm talking just about the experience that I am having right now in the research group I am working with. But I feel like both have their advantages. Both are different in the way that in France, the rights of the worker are respected most. Maybe this is good for Europe, right? They have good rights for workers. In the US, they work on Saturdays, on Sundays, they work during the night. And this is not necessarily good, but it's good in the sense that things move fast. So if you need an answer, they will answer you in the midnight. This is not good, personally, from the worker's standpoint, right? But this makes things to move fast.
Here we have a comment about additive manufacturing, and that it's
yes.
That is a very interesting topic. So what can you say is the future for this technique for reforming the way we make batteries in the future? Is it the important road to take, or what is your opinion?
Yeah, I think additive manufacturing. So normally when we think about 3D printing, additive manufacturing, we think about the printers that print with a filament, right? So in the chat, I see someone is mentioning the thesis from Alexis Morel. Yeah, he did this in his thesis. So this is the most typical way of 3D printing. But 3D printing, it's a whole range of different techniques and with a different resolution, each one of them. So I think additive manufacturing will come to improve the manufacturing of batteries, because we don't have to limit to just the bigger scale, but also in the nanoscale. We have the 2-photon printers. It's just about researching how we will be able to actually produce the layers of the battery. But I believe additive manufacturing is a great way to actually produce complex shapes that we normally don't see in the industry, just because it's more expensive, right? So right now, additive manufacturing is being seen more for portable applications, just because of the scale. But in the future, I think with the constant development of the different techniques, as I mentioned, there's a lot. I think we will be able to also produce bigger batteries in shapes that we couldn't imagine. Batteries, for example, right now we are working with Northrop Grumman. It's a company, they produce satellites. So they imagine that the battery will be hidden actually in the frame of a nano satellite. It's something 10 per 10 per 10. And so the battery will be the frame. It's pretty crazy to think right now, but it was also crazy to think about sodium-ion batteries 15 years ago. So it's natural that they will come. The additive manufacturing techniques as a manufacturing of batteries.
Especially for specific niche applications, I'm sure.
Yeah.
How about NASA? Is a question in the chat. Tell us about NASA.
Yeah, that was very unexpected. Our boss here at UTA, so he is very well connected, and I arrived to a NASA meeting just by coincidence. I was invited. It was the wrong name, but I actually get there, and I started to talk with also my colleague Alexis Morel, and we started to talk about what the ideas we have for NASA. And so they liked the idea, and they said, can you talk more about that next week? And that is how the collaboration actually started with us. And then they want actually to use in situ materials. They want, I lost my video. Yeah, okay, so their aim is to use in situ resources from the moon, so they don't have to take all of the batteries from the Earth. So they wanted to use the regolith, the lunar regolith that is full of sodium, not that much, of iron, of different oxides, of silicium as well. So they wanted to use these to produce some batteries in the moon. And because we were already talking about something that was crazy, right? Producing batteries from regolith, they said, why not 3D printing? Because we were already talking about 3D printing of lithium ion. So they said, let's do sodium ion. So this internal NASA grant, it's funding crazy ideas. Like, they don't know if these batteries will be able to be in the moon in 10 years or 20 years, but they are taking the risk to fund it, which is very valuable, because otherwise we wouldn't know, right? If this will work at some point.
Beautiful. What a wonderful story. How something can make you disruptive. We always say that in Europe, that we should have a mission to put like the man on the moon, but we talk about the green battery, not on the moon, but here.
Right.
It's a little bit of a mission. So you have a lot of experience of the educational system now in Europe, and how should we inspire young people to go into this field and really study different kinds of battery, with battery materials, but because of batteries in systems and so on? What do you think would be the key sort of golden expressions to make them really find it exciting. Of course, NASA, but that's very specific, special. Have you any thoughts about that? How
Yeah.
to people?
Yeah, thank you for this question. Yeah, in fact, I think everything is about opportunities. So if we create more programs that deal with energy storage, students will be attracted, because we know this is the future of, I mean, we cannot have renewable energies without having something to store them with. So I believe, as you mentioned before, I come from the program MESC. I believe that these kind of programs are very valuable to attract students from abroad, Europeans as well, of course, and abroad to study, to actually be prepared in this energy storage field. I didn't mention, maybe, I am originally from Mexico, and the European Union actually brought me to this program. So I believe is these kind of opportunities is what will actually attract the students to come, because otherwise I was super interested in coming to Europe, but I didn't have the resources. So if it was not because of these fundings, I wouldn't have come. So I believe that creating the opportunities is what will bring the talent. And also, I think once we are here, what is important is to have these links to the industry. Because in the lab, sometimes, for example, when I was in my master internship, I was dealing with something very specific, right? Something, I was researching something, but I was not imagining, or is not, the link is not direct to when I will see this in the application. And when I entered in the PhD, they told me, this is your topic, and we want it in the car in 2024. So this is the vision that the industry gives to the students, to actually see that what you're doing matters and will be one day in something, or maybe not, but at least you will contribute to the whole research that will bring innovation at one point. So I think this connection with the industry, it's also important to see the students have some opportunity to see what they are doing is actually going to be in the real application.
So having inspiring research, but also meaningful ideas, that combination is very good then.
Yeah, I believe so.
Yesterday, in another session, it was said that working on batteries is sexy. Would you agree to that?
Well, it is a hot topic, so
So
yeah, I think so.
Yeah. It's also so that you have comments here from the current MESC director, also the director of Acidbase, Christian Masqueli. He sends his love and congratulations.
Thank you.
But he has a great idea, and that is actually, maybe you could allow us as the 5 battery groups plus Acidbase to have you as an ambassador to really inspire young people. You made a small little film on just a few minutes that I know that the Battery Innovation Days will use for promotion, and maybe we can go back and do more together with you.
Of course, I will be happy to contribute. You know, every time there is a platform to express ideas and to motivate the students, I find that very enriching. And also, I think I can give a perspective because I just recently graduated, so I think I can give a perspective to students that are currently finishing their PhD, and maybe they don't know what to do in industry, academia. Yeah, I will be happy to contribute always.
It sounds like a fantastic ending of this prize award workshop, and thank you for a beautiful presentation. You didn't get many questions about your work, but you ensure, I'm really sure that you inspired all of us that have listened. And again, a huge congratulations and good luck in the future. We will follow your success around. And I couldn't help
Thank you very much.
this question, being Swedish. 20 years from now, when I'm allowed to, to nominate Nobel Prize laureates. And 20 years from now, when I nominate you, what should I nominate you for? What is the sort of dream that you would discover?
Oh my God, that's just such a big thing to say. It's in my wildest dreams. I haven't thought about it, but I think the battery that lasts for I don't know. I dream about the integration of the conversion of energy, for example, photovoltaics, at the same time of a battery. So this hybrid that lasts just that you don't have to plug, right? It's just there all the time, working, storing, and giving when they need you. There's research already here. So I dream with being like having this big discovery. I don't know.
The battery that lasts forever and that would
Of
function on
course.
Mars. Yes.
Yeah, right. In Mars. Oh my God, that's
I look
crazy.
forward to be able to do that a few years from now. And don't
Thank
wait
you.
too long because I'm not that young any longer. So, but congratulations and thank you so much. And by this, I end this session and also remind you that you should come back 9:30 tomorrow. And it will be an exciting discussions about digitalizations, but also discussion about what kind of topics should we actually promote for new calls in the framework of 2023 and 2024. So, and then you might get opportunity to find funding in the future that you can actually recruit Anna back to Europe. So thank you all so much. Bye-bye.
Thank you.